As I move the mouse joystick down, the elevator moves up and nose goes up. As I move it up, the elevator goes down and nose goes down. As I move the mouse joystick to the sides, the aileron move to the opposite side, and so does the nose wheel. To take off, I will set the takeoff power to maximum, lower the flaps for 10 degrees, and release the brakes. Now I will try to keep the nose aligned with the center line of the runway. We can see that the airspeed is increasing. As I reach 70 knots, I will pull the mouse down to make the aircraft lift off the ground. As we're climbing, vertical indicator shows positive numbers, airspeed is decreasing, and altitude is increasing. As we descend, the vertical indicator shows negative numbers, airspeed is increasing, and altitude is decreasing. Now I will look into the aircraft's relationship between payload, takeoff distance, and takeoff speed. First takeoff is with payload of 296 pounds, and we can see that the takeoff speed is 75 knots, takeoff distance is 1500 feet, and the second takeoff will be with 600 pounds. Flaps down, brakes off, unpause the video, and we can see that the aircraft is accelerating much slower than the first takeoff. As I reach 75 knots, I will gently pull back on my joystick. We can see takeoff speed is now 77 knots, takeoff distance is 1870 feet. It's gonna be 900 pounds for the last takeoff. Power, flaps down, brakes, and unpause the video. We can see that the aircraft is barely moving with the higher payload and is accelerating very slowly. As I reach 75 knots, I will pull back on my joystick again, and the aircraft is barely lifting off the ground. The takeoff speed is now 78 knots and the distance is 2530 feet. In this part, I will take a look into the relationship between airspeed, angle of attack, and lift. Now I'm flying straight and level with airspeed around 93 knots and the lift on the left wing is around 600 pascals. As I start to climb, you can see that the airspeed is slightly decreasing below 90 knots, but the angle of attack has increased, so that caused the lift on the left wing to increase to over 700 pascals. As I keep climbing, the airspeed keeps decreasing and so does the lift. You can see that now the lift almost disappears and it's only around 300 pascals on the left wing now. The aircraft is now stalling, so I will push the nose down to recover from the stall and gain some airspeed. The wing won't generate any lift while the angle of attack is 0, regardlessly of the speed, so I will need to pull back on my joystick to recover. Now I will demonstrate how does a retracted landing gear and flaps affect the airspeed and lift of the wing. In clean configuration we get airspeed of 204 miles per hour, and once the wheels are out it drops by 12 in just 3 seconds due to increase of drag. Now if we continue for 60 more seconds we get airspeed drop of almost 40 miles per hour. Once the wheels are retracted, the airspeed starts rising again to 180 miles per hour. Now we got a lift of 1400 pascals on the left wing with flaps retracted, and as I put down the flaps we can see the lift rising over 1600 and the speed is again decreasing below 150 miles per hour. With flaps retracted the airspeed is rising again because of reduced drag and the lift is dropping below 1400 pascals. Now let's try to land. I'm at final with 1600 RPM, airspeed around 80 knots and descending at a rate of 500 feet per minute. The poppies are half red, which indicates correct glide slope. I can adjust the throttle to make altitude corrections. For a smooth landing, I will flare the aircraft just before touchdown. Once on the ground, I will set the power to idle and apply brakes. With full flaps we can approach safely at just 60 knots, while RPM is 1500. I will finish the approach with my eyes on the poppy, and after touchdown I will set the power to idle and apply brakes.
Now let's focus on center of gravity and stability. As I pitch up, the lift arrows move up. As I pitch down, lift arrows point down because of negative angle of attack. Notice that it's the other way around on the horizontal stabilizer. Now let's take a look how the center of gravity affects the forces on horizontal stabilizer. I'll move the center of gravity all the way to the front and increase payload to make its effects more visible. First, let me accelerate to my reference airspeed to make the results as consistent as possible. I will use around 110 knots. The elevator deflection is minus 7.64 degrees, and after 2 more trials I got average of minus 7.9 degrees. Now I will set the center of gravity all the way aft, and you can see that the aircraft starts pitching up immediately. Now I will stabilize the aircraft into level flight with around 110 knots. The elevator deflection is around 1.9 degrees, which was the same as average after 3 trials. For today's lesson I have created 5 airplanes with different wingspans ranging from 10 to 50 feet. Each of them has a different aspect ratio, and I will demonstrate how that affects the lift and therefore takeoff distance. To keep the video shorter, I will show only the 2 most extreme examples. First one with the wingspan of 10 feet and aspect ratio just above 2. As you could see, the plane took ages to take off and used almost the whole runway. That was because reduced surface of the short wings and higher airspeed was required. The takeoff distance was just a little over 5800, which was the same as average after 2 more trials. Now let's try with my maximum wingspan of 50 feet. The aspect ratio is now just over 10, and you can see the airplane lifts off much earlier than previously. The takeoff distance was almost 700 feet, and after 2 more trials I've got an average of 660 feet. The data from the remaining takeoffs show us that the takeoff distance decreases as you increase wingspan and aspect ratio. For the next lesson I have created 3 airplanes with the same wing loading, but various total weight, chord, and wingspan, and we'll see how these values affect the takeoff distance. The first aircraft has total weight of 2,500 pounds, aspect ratio is only 1.5, and wing loading is 16.67 pounds per square foot. The average takeoff with this airplane was 1,339 feet. The next aircraft has the same weight and wing loading, however the aspect ratio is now 6. The wing is now more efficient and the average takeoff distance was 974 feet with this airplane. The last aircraft weighs 10,000 pounds, the wingspan is 60 feet, aspect ratio and wing loading remain the same as previously. Because of that, the aircraft should be theoretically able to take off at the exact same airspeed as previous aircraft. However, the increased weight makes it hard to accelerate, so the takeoff distance was on average 5,943 feet. For the next lesson I've created 3 new airplanes with various horsepower. First one with 150, second one 250 and the last one 350. The key objective of this lesson is to find out how the change in horsepower affects the speed in level flight. So I flew level for 3 minutes to let the airspeed settle down, and after 3 trials I got average airspeed of 134.7 knots. The second aircraft is exactly the same, only its horsepower is now 250. I'm once again flying level for 3 minutes to let the airspeed settle down. After 3 trials I got an average airspeed of 166 knots true airspeed. The last aircraft has a horsepower of 350. We can see that the aircraft is now very powerful as the airspeed indicator approaches never exceed speed. After 3 trials I got an average true airspeed of 184.3 knots.